Okay, so in this part of the lecture, which is lecture number 6, we are going to move on to path and motion generation synthesis. We had looked at crank rocker design so far. So let me just recap. We had just completed designing a crank rocker mechanism. We did this for varying time ratios, which could be greater than, less than, or equal to 1. And what you should have realized is that unlike analysis that you had done so far, there are several solutions that exist for the same design requirement, right? And of course, we briefly talked about transmission angle as a criteria which you can use to eliminate some of these designs because they may not satisfy that requirement. But effectively, even with satisfying the transmission angle requirement, you could have several possible choices, right? So which is the thing about design. Design is not unique. Now, we did a case where the rocker extreme positions we defined to be 70 degrees apart. We chosen the size of the rocker to be approximately about 50 mm for most of our designs. Now, I signed off by saying we'll recall the second and third design problems that we are going to look at in kinematic synthesis is path generation. So we'll just replay this video that I had shown you in the beginning, right at the beginning in the introduction lecture, where we want a point on a body to trace a particular path. So this we did earlier, if you recall. Yeah, so this is the video playing out. You can see that already as it comes along, maybe a little better over here. So if you watch the feet, a point on the feet essentially is moving along a straight line. As you can see in this segment, it basically moved along a straight line. So this is something that we are going to look at. How good we will be able to do that is a good question. So the design question one can pose is how to design a mechanism such that a point on a link moves along a particular path. So as I said in the video, you can think of a point on the foot moving horizontally, but we are going to do this over a limited range. We are not going to make this move along a straight line for all possible positions, only for a certain finite number of positions. So that's something that we are going to do. The other problem that we said is to guide a body through positions. I showed you the boot of my car. We'll go back and look at that video again. So here is the car boot which is being closed. So this is the open position, fully open position. The mechanism is already visible to you. So here is the way the mechanism moves, and then here we go. We close that, right? So the question is, how do I act like a Tata Motors engineer and then come up with the design of this mechanism? So that's the third thing that we are going to look at, right? So we'll only, of course, what we are going to do is, although the boot essentially has infinite set of positions going from fully open to fully closed, we are going to use only a finite set of intermediate positions, the starting and intermediate positions to basically do the design, right? So these are the two things that we are going to look at in the next couple of videos. So I remind you again that we are not going to do type synthesis, which is to find the right type of mechanism given a design requirement. So whether we need a linkage, we need a cam follower, a gear mechanism, whatever the combination may be. So we are limited ourselves to 4-bar mechanisms, and we want to understand how we can use this 4-bar mechanism to basically do path generation and motion generation tasks. Okay, so as I repeatedly pointed out, even in the crank rocker design, what did we do? We did a graphical method of designing the crank rocker. We are going to follow the same approach. The analytical approach is much more complicated. So what we are going to do is look at path generation, and since we want a point to move along a particular path, which is non-circular, hopefully. If it is circular, of course, the output rocker could be used, for example, to trace a part of a circle. But a more general motion is only possible using the coupler, because the coupler is the one that does both rotation and translation. So therefore, we are going to involve the coupler of a 4-hour mechanism, and then we design a 4R mechanism to make a point on the coupler to take 3 selected positions. So we are going to limit ourselves to 3 positions. The reason for that is the graphical method is then quite easy. If I go to 4 positions or more, then the graphical construction is not so easy. So we are going to limit ourselves to 3 precision design, as it is called, for both the path generation as well as the motion generation, because the graphical construction becomes quite easy to do. Alright, so we are going to do this with 3 precision points, and you guessed it, we are going to look at P1, P2, P3 are the points that I want the coupler, a point on the coupler to go through these 3 points, P1, P2 and P3, which of course lie on a straight line. But we are going to demand in these 3 positions, a coupler point should coincide with this P1, P2 and P3. So what are the design choices you can make? Again, like the crank rocker cases, you can look at the either design for the position of the fixed pivots O2 and O4, which means that we then decide what the floating pivots are going to be, or the location and orientation of the fixed link. So you can look at the design fixed link pivots. So in which case now I am selecting effectively O2 and O4. So in this particular case, like the second crank rocker design, I decide what is O2 and what is going to be O4. So, and also the orientation of this, which in this case I have chosen conveniently to be horizontal, right? So so in that particular case, then the design that we have to do is to basically find out the crank length as well as the distance between the point A and B are basically the floating pivots. So what is the distance between A and this point P is something that we are going to do. So so these are the two design parameters. So for example, here I have chosen a crank length. So we first chose O2O4. So now I have chosen a crank length which is some 12 millimeters, and then A1 to P1, which is the distance. It gets decided by this initial orientation of the crank, where I assume that when the crank is at A1, the coupler is basically coinciding with the point P1. So we choose A1 as the crank position corresponding to P1, and what we are going to do, so what that means is that the distance AP is fixed, right? Because this is A is, remember, is a floating pivot which is part of the coupler as well as part of the crank, which is the joint between the coupler and the crank. So since it is a point on the coupler, that distance AP, this point P on the coupler is now coinciding with P1, which means AP is fixed. Now, so using this idea that AP is fixed, we can locate A2 and A3 are located appropriately, and you have to ensure that they are sequential, because we want to go as the crank rotates from A1 to A2 to A3, the coupler point has to go to from P1 to P2 to P3. The order cannot be switched. So therefore, the task now is to how do you find B, which is the other floating joint of the coupler, and then complete the design, right? So we rely, as you all have seen already, we are extensively going to rely on the concept of inversion, kinematic inversion. So what we are going to do is we are going to assume that the coupler is fixed. So the coupler is fixed, and that too it's not fixed in any arbitrary way, but fixed in the position corresponding to 1. So that means the AP line basically is held fixed. So A1 P1 is going to be fixed. Now if the coupler is fixed, what is going to happen? The original fixed pivots, if I were, so essentially we have moved the observer from the fixed link, which is O2 O4, to A1 P1, which is the coupler. So if I were to sit on the coupler, what do I notice? I notice O2 O4 now moving, rotating basically about A and B, right? So O2 rotates about A, and O4 will basically rotate about B. So this is the motion that we will get when we work with the when we fix the coupler. All right, so I have drawn this schematically here. So how do you construct? So the idea is what will happen when, for example, I have drawn now from the previous scenario, I have the original position is O2 A1 P1. So this is the line that we had, and when I go to, if I draw a line, so the way that I figure out, remember I said AP is a fixed distance, right? So from that perspective, I can look at from P, I can draw a line of that distance where it intersects, gives me A2. Similarly, from P3, if I draw a line A3 P3 whose distance is equal to A2 P2, which is equal to A1 P1, I can locate A3. So you draw a line of so essentially cut an arc. So you measure AP. So this is where we are going to hold the coupler fixed. So A1 P1 is going to be held fixed. But if it the original scenario where the system is such that O2 O4 is fixed, this would be A2 and the corresponding P2 on the coupler, and we got that A2 by going to P2, making an drawing an arc which intersects with this circle at this point, and we get A2. Similarly, we go to P3, cut an arc of distance AP, and then this is A3. So this is basically the uh, how you will get the three positions. Now we want to do the inversion. So in the inversion based construction for position 2. So now actually I don't have this kind of a schematic where O2 is fixed. Now I have to visualize a case where O2 and O4 are moving. So that means the coupler is fixed, A1 P1 remains fixed, which means it is fixed in this position. Now I ask the question, what happens to O2 when the crank is essentially in this position? So obviously the crank moves from here to here, then what happens to the O2? Now since A1 is fixed, what we do is we measure, so we mark, so in order to be able to locate the new position of O2, so this is O2 1, if you want to call that, is where the coupler has been frozen at this position 1. Now I want to find O2 2, which is the new position with in the inversion with the coupler basically fixed at A1 P1. So what we do is we measure the angle difference. So you can see here O2 A1 P1, that line, the angle between those lines is measured. So in the case that you see there, we have about 55.6 degrees for O2 A1 P1, and when we go to the second position O2 A2 P2, the angle increases to about 75.3. Now since A1 is fixed, we now rotate O2 A1 O2, we have to rotate. So if I look at this, I will have to rotate. You can see the sense by which I have to rotate. I have to, so the angle has increased to 75.3 in the second position. So basically I have to rotate this angle that is made, I have to rotate the crank by this additional, what is the difference, is about roughly 20 degrees, right? So I have to rotate it, and since I have to increase it, I have to rotate it in the clockwise direction by that 20 degrees so that I can get the new configuration. So I rotate A1 O2 clockwise by that angle. So when I do that, so which is very precisely 19.6 degrees. So when I do that, I get the new, so of course my crank length has already been fixed, so therefore I get the new O22, right? So this gives me the new position of O2. So we do the same exercise, and of course the question, okay, so now I got O22. So by rotating A1 O2 by the angle, so that the this now mirrors basically the new increased angle in that second position. So this gives O22. Now we draw from O22 as center, we draw an arc, draw an arc of radius O2 O4. We also draw an arc from P1 with radius P2 O4. So remember that the original position P2 and O4 are at a particular distance. So we map that. So essentially to locate the new position of O4, what we do is we draw with O2 as center, we draw an arc which is going to be of radius O2 O4. Obviously that is that has to be maintained. And what you also have to realize is that from P1 we are going to draw, remember now the coupler is fixed, from P1 we are going to draw an arc whose distance is basically the length of the arc is basically going to be given by P2O4, the second position distance. So that gives us O42. So please remember, first we are going to rotate the crank by the additional angle and get O22. Once we get O22, we draw a line, draw an arc of length O2O4, and that arc is intersected by another arc drawn from P1 whose distance is basically P2O4. That gives us O42. Now we repeat that exercise for the third point. Now you can see that I have changed 55.6 to the angle has increased to about 113.3, which is roughly about 45 plus about 58 degrees. So we rotate A1. So again the angle has increased. So we rotate clockwise and then locate the O23. So here we have rotated by that 57.6 degrees and we get the O23 position. Now we do the same exercise in order to locate O43. Again do the same exercise, draw an arc from O23 as center, distance is O2, O4, and similarly from P1 the distance is P3, O4. So we get O43. So once you get so now we have, so at the end of this exercise we now have in the inversion we have O22, O23. Similarly we have located O43 and O42 and O43. So these are shown here. So these three positions are basically shown. So you can see that it intersects almost there. So O4 is O41 effectively, O42 and O43. So similarly we connect we also connect. So what we do is okay, so why are we connecting this? Please remember that we are going to draw perpendicular bisectors. The intersection of these will essentially give me B1, because remember B is at the same distance from all these 3 points. So how do you find a point B which is equidistant from this? Because that's the rocker. O4B is the rocker. So therefore if I draw the perpendicular bisectors of O4, O42 and O42, O43, which is what I have done here, I get B1 dash, B1, which is basically the output floating pivot location. So B1 is the intersection of is the center of the circle that is passing through these three, which locates the rocker floating pivot. So now we have essentially a design. So we have located B1. So remember that the whole idea of this construction, we are not interested in O2, the perpendicular bisector of O2, etc., because we have already located the pivot A. So that is not something that we are interested in. So we now have B, which means that we can complete the construction. So remember the sequence, we started off by fixing, so we said we need to design a coupler to go through 3 positions, P1, P2 and P3 for path generation. A point on the coupler should go through this. Then what we did is we said, okay, let me select O2, O4. We did that. We also selected the crank radius and then an arbitrary position at which the crank should sit for A1. And then what we did was basically assume that as though the coupler was fixed at the position A1, P1, and using the principle of inversion basically found out what positions O2 will move to in corresponding to P2 and P3, and then we got the other floating pivot location B. So once we have that, we have the design here. So in this particular case, I have a design where L1 is 220 mm, so 22 centimeters, not millimeters as I mentioned before. L2 120 instead of 12 mm as I mentioned before. It turns out L3 is 292.6, which is the distance between A and B. And of course the L4 is kind of small now. So you can see actually that becomes my kind of crank, and it turns out to be Grashof, fortunately for me. And this is the coupler point that we have. All right. So I have, you can see before I animate, actually this is the locus of the coupler point. And you can see we thought we'll get a straight line, but unfortunately you can see that while the coupler does occupy those positions P1, P2 and P3, I don't quite get a straight line. So let's go through this. The O4 is now the crank of this mechanism. So you can see that it does, the point F does goes through the three coupler points P1, P2 and P4, P3, but unfortunately it doesn't come out as a straight line. Let me play that once more. So you can see that it is coming down, passes through P3, but then it is not, the three are not actually on a straight line. You can see that P1 to P2, well, you could say that it is almost a straight line, but the thing is that the design criteria was that the coupler should occupy those three positions, which it does, but unfortunately our original thought process was that P1, P2, P3 should be a straight line. That didn't happen for us. All right. So the designed mechanism does pass through the three precision points. However, the motion between the 2 points is not along a straight line, which is one of the disadvantages of precision point based design. One way to take care of this is to increase the number of precision points, which will work, but we are not going to do this because it's graphically very difficult to do, and you have to resort to analytical methods to do so. um, in the next lecture, what we are going to look at is how to do path generation with timing. We will define what we mean by timing. So we have done a general path generation system here, and you could do this with timing, and we'll specify the input link angles with respect to the position 1 like before. So what do we mean by path generation with timing, I will define, and how do we go about doing that kind of a design, we will do. Okay, so with this I will stop my video.